Is it recording? Oh, recording about to start. Cool. Okay, it's recording. Um, where is sharing my screen? I think it's that. Share screen with audio, start broadcast. Wait, hey, can you check for a second if my screen is being shared? Check in the HCAN Teams if my screen's being shared currently. Bet. Cool. Would you like to get started or would you like to wait a little bit? Nope, people are coming, so more people. Cool. How's it going, y'all? How we doing? We got four people. We've met last time. We've met the same amount of time, or same amount of people. Oh, the freaking nano VNA?
The useless fit nano VNA?
Yeah.
Yeah.
All right. Would y'all like to get started or you want to wait a little bit? I don't care. It is starting to be recorded.
I was gonna say, it's recorded.
So, well, yeah, that's fine. Okay. All right. I'll get started. So I plan on doing an active filter problem, a two-port problem, and a single phase problem, which is all the three things that are going to be on y'all's test. So,
Do you know that for?
well, he just
You just
told me.
Yeah.
Now the two-port problem that I will be doing is more of a model. So we'll be analyzing it and doing it, using member name, whatever, and then whatever he asks, we'll be doing that. Now the two-port properties, um, just do it like your problem set and kind of do it that same way. Just keep those solutions on hand so you can look at them during the test. It should be good. So, Pablo, you want to interject anything before we get started? No?
I would say, read on. I'll get this for you first. I'll do your final. Pay attention to his handwriting too. Yeah.
I say everything that I will write.
Doesn't
So,
say, but call, but then. Read like the same thing,
that's why hey, this is being recorded right now. Thanks so much. Okay, well, I'll get started. So we'll do active filters first. Okay, so I'm gonna read it. So the op amp circuit shown in figure 93 is the topology for yet another salient and key active RC filter. The op amp is assumed to be ideal from analysis equation, developed in a handout. The voltage ratio transfer function is given as that. If anybody also wants to take a photo of this, you're more than welcome to. Where Y of S is the S domain admittance of the filter components. Apply the component types and values shown in the schematic to this formula to generate the biquad transfer function for the filter of the format this. So K in the S, and currently it says we have an in, and then the denominator is going to be S squared plus omega P over QP times S plus omega P squared. That's important. Where KXX, it also has that, sorry, is the biquad scale constant with XX denoting the biquad type, i.e. LP for low pass, BP for band pass, and HP for high pass. And omega P is the pole frequency in radians per second. QP is the pole quality factor, and NS is the numerator polynomial. For this format, from this format, A, define the biquad type as in low pass, band pass, or high pass, and calculate the values for the K, XX, omega P, and QP. Okay, so can anybody tell me what this is? So it's an active filter, right? What do we do in these type of problems? Where do you, what's something that you look at this problem and you go, okay, this is where I need to go. What do you do? Book 3, Chapter 2. That is your best friend for this type of problem. So in those problems and a lot of stuff that you've done in the problem sessions, right, or problem sets, it's stuff that he's already denoted as, and if it's a high pass, a low pass, or band pass. Well, we don't have that yet. Okay, so what do you think we should do to figure out, hey, if it's a low pass, band pass, or high pass? What do you mean by Z1, Z2, and Z3? Do you mean the impedances?
Yeah.
Okay. Yeah, I agree with you there. I like that idea. For this problem, sadly, that's not going to work. Another way you can do that is the numerator. The numerator is going to tell you everything. There's three type of filters. There's three ways your numerator is going to go. You're going to get a term. Let me look at this. I'm also looking through book 2, chapter or Book 2, chapter 3, that's what it is, yeah. So for a band pass, or for a low pass, your numerator, okay, well, never mind. I gotta get to the right part of the thing. I gotta go through 115 pages. Let's go.
That's where these sets of problems are located.
Yep, book 2, chapter 3.
Book two, chapter-
That is gonna be your best friend. Yep. I'm gonna actually go to that real quick. Okay, so first off, this is a negative feedback topology. Best way to put it. As if you look here, you have the feedback. Let's see if I can write some stuff. Is this writable? Sure. Let's erase that. So you have stuff going in the negative, you have stuff going in the positive. If we go back, stuff going into the negative and stuff going into the positive. We'll just do that. Multiple feedback. Right. So if we're going back down, here we go, here we go, here we go, blah, 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 blah. So that's an overall equation right here, as it's shown earlier. This is from last semester when I did that. This equation is not the same as that equation. Go with the equation on the paper. Go with the equation on the paper. So here we have a low pass, okay? And as I said, we look at the formats. If you look here, there's a low pass format. What's in the numerator? Omega p squared. So if we have a term where it's just a numerical value, it's going to be a low pass format. Does that make sense? There's no S. You don't see an S in the numerator. So low pass format. And this part, what page? This is page 41 out of 115. I don't know if this you don't want to write that down, but for low pass in terms of multiple feedback op amps, page 41 is going to show you what the low pass format is. Okay, now I'm going to go back. Now we have the multiple feedback band pass. And as you see here, band pass format. What's in the numerator? Say that again. Yeah, exactly. So a singular power of S is going to give you a band pass format. And that's on page 43. That if you want to do that. And then finally, high pass. You're going to have, what's in the numerator? S squared. So that tells you what you have. S squared is high pass. Something times S is going to be your band pass. And then just a numerical term, period, is going to be your low pass. Does that make sense? Low pass was 41. The band pass was 43. And high pass was 47. Okay, so I'm going to go back to the equation, or going back to here, okay? So as you can see, we have an R1, we have a C2, we have an R1, we have a C2, we have an R3, we have an R4, we have a C5. We also have this resistors RA and RB. I'm curious, since y'all haven't really done op amps, if you can answer this question. What type of feedback is this op amp? Positive feedback? Are you sure? Well, actually, it's multiple feedback. That was a bad answer. But these resistors here are telling me to use a certain feedback equation. It's also found in book 2, chapter 3, but it's kind of hard to find. Yeah, so as you can see in this term, we have this mu A. Okay, well, we don't really know what mu A is yet until the equation for it, basically this feedback topology here tells you that mu A is equal to 1 plus RA over RB. That is what that tells me. That's also in book 2, chapter 3. I gotta find out where that is. Give me one sec. Yeah, this book 2, chapter 3 has everything you need for these type of problems. It's just gonna be convoluted to find it. How's it going? Here we go. Is this type? Oh, I'm an idiot. You could have just done that. I could have done that. Okay. Well, this is found on page 9 of that book 2, chapter 3, where it shows the op amp thing or the gain where mu A is. Uh, and it's the same topology. Yeah, that RA, RB. Now the Z's are a little bit different, but that don't matter. All right. So we found that mu A equals 1 plus RA over RB. That's it. So when we plug in those values, it'll just be 1 plus RA in this case is 550 over 1,000. And then mu A becomes, I don't want to put that in a calculator. I'm just going to put that 1.55. Okay, so we have a bunch of components, okay? And the equation given is a bunch of admittances, okay? Does anybody have any thought of as to what we should do next in terms of how to solve that equation? We have a bunch of components. We have numerically assigned components.
At this point, you can just, you have mu A and all you do is you convert your individual components to their admittance
Yep.
values and then just plug in one more.
Literally that. So I'm just going to denote everything. Okay, we have a Y1, right? 1 over R1, which when you put that in, becomes 3.33 times 10 to the negative 4th Siemens. You have a Y2 equals S times C2, which equals S times 34 times 10 to the negative 9th Siemens. Y3, right, is 1 over R3, which just becomes 10 to the negative 3rd Siemens. Y4 is 1 over R4, which becomes 1.667 times 10 to the negative 4th Siemens. And Y5 equals S times C5, which equals S times 17 times 10 to the negative 9th Siemens. Well, he said plug it in, right? Well, you could by hand plug this into the calculator, or I'm sorry, you can plug it by hand, play everything, blah, blah, blah. But I don't want to do that. I'm literally just going to chug it into this thing, right? So does everybody have a TI Inspire or anybody have access to a TI Inspire? Does people who don't, do you know how to get access to one? Does everybody in this room have access to one? I'm just curious. Yep. Okay. So there's a handy dandy function on here called storing a variable, and it is your best freaking friend. Okay. If you look at your number pad, right? Look at the numpad on your things. Look at the 9. Look at the value right above it. Okay. Does anybody? I'm just gonna show you right there. There's the 9. The value, it says VAR, but if you see in the blue text right above it, it says STO. That stands for store. Okay. So let's say I want to put this value Y1 into the calculator. Okay. It's 3.33 times 10 to the negative 4. All I do is 3.33 times 10 to the negative 4. Okay. Control, hit that button, denote it as Y1. And now when you type Y1 in your calculator, it'll give you that value. That simple. Can everybody see that? Does anybody want to look at my calculator to see it? If anybody wants to come up and look at my calculator, more than welcome to. Does that make sense? So like for Y2, I hit S, and anytime you're using any numerical value, you have to multiply. You have to specifically multiply. You can't implicitly, as in like S and then write the thing, you have to write S times. So you'll put S times 34 times 10 to the negative 9th, control store, and then you'll denote that as Y2. And it'll give you a value. You can do this, you'll do it for all 6 things, and then literally plug this formula in. So you'll type in, G, what is it, G of S equals, write this from here. Okay. So mu A Y1 times Y2 all over Y1 plus Y3 plus y5 times y2 plus y4 plus y2 times y4 minus mu a times y2 times y3. Okay. And so you literally just plug all those different variables, you store all those different variables in your calculator, type it up, and you will literally get this equation. This, I literally plugged it in, and when I plugged in all those values, this is what my GV of S looked like. 30.392 times 10 to the third S over S squared plus 1.961 times 10 to the third times S plus 384.468 times 10 to the sixth. Can anybody tell me what type of filter this is? Well, okay. Anybody have any questions so far on how I did that? Y'all saw I stored them in my calculator, literally just typed it out. Yeah,
You said this is exactly how it came out.
that is exact.
On your calculator.
I think I hit Control Enter, and that's what came out. So, yeah, if anybody's curious after the review, I can show you how to do that. I don't mind spend some time on that. But yeah, so we have a numerator, and we also, if you notice, we want to get it into that form in the denominator where we have an S squared plus A1S or A2S, sorry, plus A1. Like that, that's this. S squared plus A2S plus A1. That form look familiar? We want to get the highest form of S by itself. Y'all recognize that? So as you notice, my denominator is there. Is how it is. And if you get something where you don't have that, where your highest form of S is not by itself, you need to normalize everything. You need to get that highest form of S by itself. That makes sense? Okay. So, well, we have a numerator now. What's in our numerator? Exactly. So based on what I said earlier, what type of filter is this? Is this a low pass where it's just a numerical value? A band pass where there's one form of S in the numerator? Or is it a high pass? Band pass? Everybody agree? Does it make sense? I agree. It's band pass. So I'm just gonna write that. Band pass. Yay. I think that's literally just part one. Is that literally part one? Okay. Define the biquad parameters. Band pass. And that is because, as we just noted, why is it band pass? Exactly. Okay. So the numerator, or the denominator, right, has the form of S squared plus omega P divided by QP times S plus omega P squared. Well, we have to find these values. K, XX, which we denoted as what? What is that XX now? Band pass. Now, KBP, omega P, and QP squared. So based on what our denominator is of this S squared omega P over QP times S over omega P squared, which of those three values can we find straight up? I would just say omega P. Because currently we have a fraction, this fraction here is equivalent to that term. And I don't know either of those values yet. But this omega P here is just equivalent, omega P squared here is equivalent to this value here. So to get omega P, we're just going to square root this value. Does that make sense?
Yeah.
So as I just stated, omega P equals the square root of 384.468 times 10 to the sixth. And when you plug that into your calculator, omega P becomes 19.608 kiloradians per second. That's simple. That's simple. Okay. Now, what do you want to do next? Exactly. So if omega P, by the way, y'all understand the S squared, that this equals that, and that equals that. That makes sense to y'all? So if we want to find the omega P QP, this term here, omega P over QP, equals that term. So omega P equals 1.6 times 10 to the third. Well, if we want to find QP, QP equals omega p divided by 1.6. Well, I'm sorry, it's not 1.6, 1.961. I'm sorry, 1.961 times 10 to the third. So then we plug in the value of omega p, and we want omega p. Russell is kind of weird when it comes to like frequency. Sometimes he just wants it in angular frequency. Sometimes he just wants it in hertz. Sometimes he wants it in both. Um, if it doesn't clearly state it, I would just recommend putting both. It doesn't hurt. How do you get from angular frequency to just frequency? Well, what do you do with the 2 pi? Do you multiply? Do you add? Do you subtract? Do you divide? Divide. Yep. So F equals omega p divided by 2 pi. So if it doesn't clearly state it, which it doesn't clearly state it, just says omega p. Well, it says omega p is the pole frequency, but it doesn't clearly state give omega p in radians per second or hertz. I just recommend doing both. Never hurts. That was no pun intended, but I heard it in the second I said it. So yeah, so whatever. That I did not put it in hertz. Just like I said, divide that by 2 pi and you'll get an answer. So QP will be that 19.608 times 10 to the third divided by the 1.961 times 10 to the third. So that means QP becomes, technically, if you have this, 9.998, which is just equivalent to 10. It's really close to 10. So, does that make sense how I got that? So also, okay, last part is KBP. So we have our numerator, which is just this value here, and we need to get it into something else. Now we denoted this as a bandpass. I'm going to go back to book 2, chapter Z, or chapter 3, book 2, chapter Z, something else. What did I say? I said 41. That's what I did. Oh, I want the bandpass, right?
Bandpass.
Yes, thank you. Low pass and then bandpass. Okay, as you can see, bandpass has this KBP times omega p over QP times S. It has that negative here. Doesn't that matter? Let me double check something real quick. Sorry. I think this is. Y'all feel pretty good about this test, or no? I mean, it's a Russell test, right? So it's like, oh, geez. I think I got this. I think this will be good.
I think he likes to talk.
Yeah, I understand that one heavily.
But if it's anything based off of the homework, then, I mean, I don't think it's
Yeah, the biggest thing is just getting it done right in that time.
gonna. Yeah.
So this one will be more straightforward. There are a few curveballs, but it'll be more straightforward.
Yeah, I was. Yeah, and then the PA, she was like, yeah, he's never given this question. It's like the people in HK and IEEE can't even solve this, or they can, but it's a lot of trouble for them to. And so
Yeah,
like, yeah, don't have to give that question.
circuits 1, I think he's a little bit harder on than circuits 2. But so going back to this negative doesn't fully matter in terms of this instance, but we see this KBP times this omega p over Q times S is going to be the numerator. So we have KBP times omega p divided by QP equals, well, what's in our numerator? This value here. So that equals that. 30.392 times 10 to the third. Okay, well, so KBP is simply 30.392 times 10 to the third divided by that omega p divided by QP. Well, what is this value here in terms of what we've already looked at? The omega p over QP. Exactly. It's this term right here, because we said this term right here. So that means that KBP equals 30.392 times 10 to the third divided by 1.961 times 10 to the third. So that means KBP equals 15.4 0.98 or 15.5, however you want to write it. That's it. We're done. It's a lot of identifying what's there, how you can plug it in, and that's it. Does anybody have any more questions on this test or for this question? Sometimes, like for this one, we had to identify what it was. Like I said, maybe he'll give you what it is, and you have to identify some other stuff. Yeah. Got you. Does that make sense how I did all that? Yes, no, yes. No, this one is no units. The only thing that'll have a unit is omega p. That's the only one that'll have a unit. So he's denoted KBP as a what does he call it? What does he call it? A scaling constant, therefore it's a constant, no units. Same thing with the quality factor. It's just like a ratio. Or it's not a ratio, but it's just a constant. So yeah.
So it says KXX.
Yeah.
Explain that one more time.
So
I understand that it means whether it's low pass, band pass, or high pass,
Mhm.
but as far as in relation to part B of the question.
Yep.
What is he looking for exactly for that?
So it's like we said, it's KXX. He is not noted whether it's a low pass, band pass, or high pass. So we have to figure out what it is, and we've denoted it as a band pass. So that KXX, it's actually a K.
BP.
Exactly.
Yeah.
So it's a band pass
Low
scaling
pass
constant.
would be KLP, high pass would be KX.
Exactly.
Okay.
Exactly. So it's just the scaling constant of your filter. And so that's when I went back to the book 2, chapter 3 and figured out which one it was. So, but yeah, these questions, I think these are not they're good to do. They're relatively easy to do. As long as you got a TI Inspire or something that can do it, you're chilling. Yep. Mhm. Okay. Sure. Yeah, sure. Whatever tells them that you understand that it's a bandpass, it should work. Yeah. Which one is that? What page? Uh, of the book 2, chapter 3? Okay. Page 11. Are you sure? Page 11? What PDF is it called?
Oh, it's 13.
Oh, I was talking about the top, sorry. Hey, yeah. You're good. You can have this back, thank you. It's not explicitly the same thing. If you see, it's not the same thing. So let me go here so I can show everybody. Here we go. So you have this capacitor and this resistors. They're in parallel. They're directly in parallel. You agree with me there? These are not directly in parallel here. You have this capacitor here. So I get what you mean in terms of it could be as simple as look at the filter. If it's the exact same thing, you're going to know it's the right thing. But in this instance, I see what you're seeing. It's close, but it's not the exact same. So that's why doing the plugging it in and finding what's on the numerator is like the most surefire way. But if he just gives you that it's a band pass or low pass or whatever, literally just look at the document and see if you can find those exact specs and see if it's the exact same. It should be good. Any more questions on this, or I was gonna go ahead and go on? That sweet.
As far as RA and RB are concerned.
Yes.
You said you looked at that earlier, and that's only like in that particular configuration, it's only alluding to the value of mu. Is that what you said earlier?
As in like
As
this,
in the
yes,
formula is 1 plus RA over RB.
yes. And then we don't do anything
And
with
then,
the RA.
and then that's all, that's.
Yeah,
okay,
that's
the
alluded.
only significance between RA and.
Yeah, because when I first saw that problem, I was like, what is RA and RB? What is that even used for? Because when I think of these problems, I think of literally just plug and chug in this type of equation up top.
Okay.
But yeah, it was literally just this factor here. I don't know what mu actually is in terms of the actual unit. I don't know what it's called. probably some,
That's okay. I was really just making sure that
you didn't have to do
mu
anything
is
else.
its own thing and RA and RB aren't necessarily alluding to what kind of.
I got you. Yeah, no, sadly, no.
Okay.
Yeah. All right, cool. I'm gonna go ahead and move on. If anybody's got any more questions, just let me know later. Oh, I didn't even use the third page. Okay, so, what type of problem, I'm not gonna read it yet, but what type of problem does this look like? Okay, single phase, three phase. I agree. Okay, so I'm gonna read it. This was from a test. This was, I think this was last semester's problem 3. So this was from last semester. Okay, gonna be honest, this could show up on your test. Hint, hint. Yeah. Okay. So the network shown in Figure 3 represents a component scaled single phase electrical network in the time domain. The source connected in the terminal AB is an AC current generator with the time domain expression for the source is written as that. The RLC network, blah, blah, blah. You're asked to calculate the values for the following. A is complex power, power average, reactive power, and power factor. B is the type and the connection of the component that will correct the power factor to unity. Show all your work and blah, 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 blah. Okay, so a couple things have been here. I got this from Pablo, so he just kind of had his scribbles on there, and I didn't know how to take them out. What's our phasor voltage, even though it's already there? Yeah, it's fine. Okay, just gonna, yeah. So what's our frequency? Exactly. Does everybody know why that, you can see why that is? Okay, okay. So what is a good idea to start? Hint, hint, it's already drawn. What tools can we use to analyze this type of problem? Yeah, sorry, drawn. Yeah. So I'm going to start using MAME. Well, what do we need for MAME? What are the components that are used in MAME? What type of sources? Current, voltage, voltage sources. What type of passive components? Resistors, conductors. Which ones? Like, if we're analyzing them, are they do they have to be resistors or do they have to be conductors? Or resistors,
Yeah.
also known as impedances. Yes, that's complex. Sorry, I should have said impedances. Okay, so I'm just go ahead and let's do the MAME. All right, I'm gonna put everything in S's, but S is equivalent to what? J omega, exactly. I like writing S's. It's neater, even though my handwriting sucks. Okay, so we have R1 plus 1 over SC1. What the heck? Where's my there? Okay. Yep. Plus 1 over SC2, sorry. 1 over SC2, negative 2, 1 over SC2 plus SL3. IM1, IM2 equals VAB, nothing else, and this becomes negative RMI2. Does everybody see how I did that? The only thing in mesh 1 is R1 and SE2. The shared is SE2, negative SE2. The only thing in mesh 2 is SE2 and SL3. If I denote my IM as it's denoted here, which I'm just going to keep the same polarity, that's how I would do it too. The VAB is positive and the RMI2 is negative. Does anybody have any questions on how I did that? Anybody? No? Cool. Makes sense. Cool. All right. So I2. Looking at I2, I'll let you all figure that out. What is I2 in terms of mesh currents? Does anybody else agree? Does anybody else disagree? I agree. IM2 minus IM1. All right. So I'm going to separate them. VAB 0 plus, I'm just going to go ahead and put it in the matrix where it's already in technical resistances. 0, 0. For this one right here, it's going to be RM, and this one's going to be negative RM. All times by IM1, IM2. And that is because right here, right, when we separate it into IM1 or IM2s and IM1s, my thing in IM1 is negative. Negative RM becomes a positive RM. My thing associated with IM2 is positive. Negative RM, negative RM. Does that make sense? Cool. All right. Putting those values over here, it becomes then R1 plus 1 over S2, negative 1 over SC2, negative 1 over SC2 minus RM 1 over SC2 plus SL3 plus RM. IM1, IM2 equals VAB and zilch. Okay. I have everything in S's. You want to put that into J omegas. And when you put the values, I'm just going to go ahead and show you my final matrix. That becomes 10 minus J5, J5, negative 2.5, and 2 minus J, all times IM1, IM2 equals VAB. Does that make sense for everybody? If I were to plug in the values for everything, where S equals, what does S equal in terms of like numerical values? We've already denoted that S equals J omega. What is omega that we said earlier? 4. So that means S equals J. Exactly. So every time there's an S, you just put a J4 and then plug in the values for your things and you'll have that. Okay. So, we want to find the complex power, okay? The input complex power, basically. And it's denoted as basically being right there. Well, what is there? There's a VAB, and there's a VAB, and there's what? Current. Okay. Well, what's an equation for complex power in terms of current and voltage? I agree, but what do you have to do to the I? Conjugate. Does everybody agree? Okay. So, I need to either find voltage or I need to find current. So I'm going to use, where am I going with this? Give me one sec. Name and M can also be used to find impedances or admittances, correct? Driving point impedance, driving point admittance. It's kind of like you're finding the total admittance of your circuit, right? What can you do? What is MAME used for? Do you find admittance or impedance with MAME? This is kind of a difficult question. Think about when you find impedance, the equation for impedance, right? Z equals V divided by R. Okay, you agree with that? So that means Y equals I divided by V. Okay, it's a little hard to see. I'm going to try to go through it, and if you got any questions, let me know. So MAME, when you use MAME, you're finding mesh currents. Okay, you're finding this part. Okay, and when you do that, you can do it by finding. You can just solve it straight up in a calculator. You can do Kramer's, but when you do Kramer's, you're gonna have, like, if you find mesh currents with Kramer's, right? You're gonna have your thing equals your what is it? Delta IJ over delta times the other thing. As in, if you're finding mesh currents, right, equals delta IJ over delta times V. If you're finding voltage, it's delta IJ over delta times I. Okay. What is our undefined here? Like, we have, all this is defined. Okay. Mesh currents, just mesh currents, that's whatever. Well, what's over here? VAB. Well, we don't have a VAB. Out of these two equations, what would cancel out? If we were to find, well, MAME, you find your mesh currents. You have a voltage. If you plug that in there, your voltages cancel out. So therefore, MAME, that's not how you spell MAME, MAME equals YDP. Flip side for name. You find your driving point impedance using name. So that was kind of a convoluted way to say that, but it makes sense because you're canceling out your unknown term, basically. So if you're trying to find something, or if you're using MAME, your eventual thing that you're going to find is your driving point admittance. And if you're using name, you're eventually going to find your driving point impedance. So does my derivation kind of make sense? A little bit. Yeah. In terms of mathematically, that is that. When you're finding your mesh currents in terms of Kramers, you're going to find that. And that's exactly how we're going to do this. So like I said, we have a VAB and an A. Well, you can't really find voltage with name, but you can find current with name. Okay. So what is what is IA in terms of mesh currents? Well, correct. IM1. Yeah. IM1. So that means IA equals IM1, which equals, technically, I forgot the -1 part, but you all know that. 1 plus 1, delta 1, 1 over delta times VAB. So that's just going to become negative. Okay. So as we said earlier, driving point impedance is IA over VAB, which then just becomes delta 1, 1 over delta. Do y'all agree with how I got that? The VABs cancel out. IA is just IM1, blah, blah, blah. So that is our final equation. What is delta 1, 1? I disagree. I agree. The way you find it is delta 1, 1 is the stuff the 1 and the 1 is the stuff you cross out. You cross out the first row and you cross out the first column, and whatever's left is what you use. So if it was delta 1, 2, first row, second column, then it would be that. So delta 1, 1, boom, boom, that's left. Does that make sense?
Under what circumstance?
Under-
Would it ever? As
Yes,
far as delta 1, 2,
it would.
I guess it was for M2.
No. It has to do with where your sources are. It has to do with where, yes, I answered this last time. Yes. Oh, crap. I'm going to forget this. Okay. It has to do with that and where your reference is. Let me see if I can jog my memory on the last one. Sorry. It's been a second since I did that. It's a good question. That is a good question. This is all first test stuff, so you're not gonna need that at the moment. Oh, hey, I did the same thing here. Okay,
I did see you scroll past it.
yes. Okay. Okay. Yes. Okay. Okay. It is delta 1, 2, as we said here. What are we even looking for in this problem? Okay, it's looking for IM2. So we're looking for IM2, okay? This problem, just short analysis. What is YT, transfer function Y, IM2 over EG, okay? Where is EG? First mesh. Where is IM2? Second mesh. It's IM2. First number, right? That I is going to equal reference. That J is going to equal what you're looking for. Where is our reference? What mesh is our reference? Where is what are we looking for? Where is it at?
But you're looking for IM2.
You testing me there, I see. But does that kind of make sense? So
Yes.
So-
Yeah. So specifically, if it's IM1, then it's reference 1, mesh 1.
exactly.
And then if it's IM2, then it's reference, because everything is based off of where the reference is at.
Exactly.
So it's reference 1, mesh 2.
Exactly.
Okay.
And so if our reference source was over here,
Then it would be 2.
1 or 2,
2, 1 or 2, 2, depending on what you're looking.
exactly. So hopefully that helped.
Yes.
And in circuits 2, in terms of Kramers, if you found a 3 by 3 matrix, I would be shocked. I would be shocked. So I mean,
I think he's told us that he wasn't gonna do that.
yeah. As far as past like Thevenins and Nortons, you shouldn't see a 3x3 because Thevenins and Nortons, you do 3 times or 3x3 sometimes, but you don't really use Kramers on those.
I just don't think there's enough time in the class for you to first.
We had a 3x3 matrix my first test. Did I finish it? No. But yeah, our RTA was pretty good. So as we denoted, delta 1, 1, first row, first column, that's all that's left. 2 minus 1. Delta in this case, you can do it by hand, you can put it in the calculator, I don't care what you do. But it comes out to 40 minus J10. Just giving you that. You can check it later if you like. So YDP then becomes 2 minus J over 40 minus J10. So YDP is 52.941 minus J11.764 milliohms. Not milliohms. I'm sorry. That's a false. Millisiemens. Millisiemens. I wrote milliohms. Okay. Okay, cool. Also, well, okay, that is that. So we're going to find voltage and current using that. Okay. Well, we don't need to find our voltage. Why do we not need to find our voltage? Exactly. It's given as EG, which is equal to 5. Okay. What's another thing that is important about these problems? We have voltage. Do we keep it in that voltage form? Do we need to change it to a different type of voltage? RMS. You need RMS. Why do you say that? I'm actually like, I'm kind of blanking on why we need RMS. It's just, I don't know if you would know that. Yeah, that's a good way to put it. Just always keep it in RMS. I agree. So
What he always does. Yeah. Yes.
sometimes that's as simple as it needs to be.
What he always does.
Yep. Well, so I've told you about that. Well, how do we find it? Exactly. So when we do that, ERMS becomes 3.536 volts. Okay. We have a voltage. We have a YDP, which is our impedance. What can we do now? What can we find with voltage and impedance? Admittance, sorry, which is the inverse of impedance. Exactly. So I RMS equals E. I'm going to write RMS. What's the relationship? What do we do with that ZD or YDP? Do we multiply it? Do we add it? Do we divide it? Do we subtract it? Multiply? Anybody else disagree? Agree? Does anybody agree or disagree? I also agree. YDP. So when you put those two numbers of this times this, you get the current of RMS equals 187.175 minus J41.595 milliamps. Okay. Well, we kind of said it earlier. How do we find complex power? What's up? Well, what do we take the conjugate of? I agree, but it's only one thing that needs to be conjugated, right? The I. It's just the I. So conjugation just means if you have a real plus JIM, if you conjugate that, it becomes R minus JIM. Just flip the middle of this one. Flip this sign, whatever works. So when I put, this value here multiplied by the conjugate of that, as in I change that value, I get an S of, sorry, give me a sec. Say that one more time. Not if, because it's an RMS, we don't. So if we were to just have E and I, yes, we divide it by 2 because theoretically, S equals E times I over over 2, right, is the same as doing, this would be, that would be the RMS value. Would you agree? That would be the RMS value. Well, what's square root 2 times square root 2? Same thing. So since we found the RMS value, we don't have to do that. But if you were just to find the current and voltage straight up, you would have to do the dividing by 2. So that's important. That's a good point. Did that make sense? So it's how wherever you want to find it. I just found it in the RMS. I'm sorry, I found it in RMS first, instead of doing that. So, yep. I'm gonna erase this real quick. Or do you want me to put that back up there, or you get that erased? All right, that. Okay. So, yeah, and since I denoted it as RMS values, we're good. As long as it's denoted RMS, you're good to keep that. No, whoa, I don't like that number. 661.765 minus J 147.059 milli. What are the units? Huh? This is complex power. Not VARs. You've multiplied voltage and current. Volt amperes or VA. I got you. So this is complex power. What does this tell us? Technically, it tells you two other things within itself. Yep. Well, I get you're saying the units. I'm just going to say the variables. So the power and complex power. Well, where's our power in terms of this equation? Which is our real part. Which our real part of our complex power is just going to be power, and that is watts. Now, why do I keep writing triple sixes? Okay. Milliwatts. And the second part of complex power is what? Reactive power. So Q, and it's just negative for the blah, blah, blah. And what are these units? Yo. Well, I'm just going to put a bar. I don't think you care. That's part A. That's it. That's it. Okay. Part B. Let's go back to part B. This one's the kind of tricky one. It's kind of tricky. We got to find the type, value, and connection of the component that will create. Oh, I'm sorry. I'm so sorry. We are not done. We are not done. Power factor. Power factor. Right. No, I was testing you. Nobody got it. No. Well, how do you find power factor? What's up? You could do that. Yep. But I don't really want to do that personally because I'm already in rectangular. So here's another form of power factor. Real power over the magnitude of our complex power. That is a legit formula. To get complex power, you take, if you were to put it in your calculator, magnitude of S is equal to typing this. So like this value of S, literally type in this formula here, ABS, parentheses, and you will get the magnitude of it. The ABS stands for absolute value of it, and that is the magnitude of S. So when I do that, when I plug that in, I plug the magnitude of this here and this here. I get a power factor of 0.976. Also, you could just do this, write this out. Keep doing it. I'm not doing great over here. There we go. 5 times 10 to the negative 3 squared plus negative 147.059 times 10 to the negative 3 squared. Same thing works. Or you could put this into, put it in polar form, whatever the angle is, take the cosine of that. It's going to be the exact same form. So it's just however you want to do it. So yeah, you could, S equals magnitude, angle angle, I'll just call it angle. And so power factor equal, call it S, equals cosine of theta. So you could also do the same equation that I did here in this form, and just your magnitude is going to be that. Does that make sense? All right. That is part A, I think. Yep, I found everything. We're good. All right. Part B. This one sucks. Okay. Unity. It said the type, value, and connection of the component that will correct the power factor to unity. What does anybody know what that means? I agree, but what does a power factor of 1 mean? Anybody else? Does anybody agree with that? Yeah. I agree with that. I'm just going to say it. Yeah, I agree. To do so, how do we get rid of complex part? Yes, you have to add the inverse, not inverse, not the inverse. Exactly. You have to add the opposite sign of whatever you have. So, okay, we found, what did we find? We found YDP, right? So our YDP is equal to, write this down again, 52.941 minus J 11.764 times 10 to the negative third. Okay. What are the two parts of adminence? What is the real part called? What is the real part of adminence? Take the inverse of that. What's the unit for C? Well, what's the variable? What's up? Conductance, which is a G. This one's going to be a little bit harder, but what is the imaginary part of your that? Yes, those will be components. So for impedance, the reactive part is called reactance. For admittance, the reactive part is called susceptance. Yeah, it's a weird word. I don't even know. I'm not going to try. I'm not going to try. We're not in friggin' English. So yeah. Yeah, this is YDP. It's also called YHP thing. It's just basically the input. Okay, so we have a negative susceptance. Can anybody tell me what type of equivalent component that is? Now, you said something about an inductor and a capacitor, right? Those are components. Well, which one has a negative susceptance? This is no. That would be the case if this was impedance. So a capacitor has negative reactance, but it has positive susceptance. An inductor has positive reactance, negative susceptance. Okay, that's just how these components work. Because y'all agree that reactance equals, J reactance equals negative J reactance equals negative J over omega C. Omega C, yes. Do y'all agree with that? Y'all agree with that? Okay. Well, what is the susceptance is the inverse of that. What's the inverse of this? Does that make sense? It's a negative. There's a negative of the entire fraction, a j in the denominator. If you put that up top, it becomes a negative j. So a negative times a negative becomes a positive. And it's the same type of thing here. It's jx equals j omega L, which if you take the inverse of that becomes then 1 over j omega L, which then becomes negative j omega L. So that's why negative susceptance, positive susceptance, because they're inverses of each other. Does that make sense to you? Okay. So if we have a negative susceptance, we have decided that a negative susceptance means it is what? Either a conductor. We have a conductor here, and we have a negative susceptance, meaning that negative susceptance is a type of component. Is it an inductor or capacitor based on what we just derived? An inductor. I agree. How do we cancel out an inductor? Capacitor. Okay. Do we even really need that value of the inductor? Let's see. The type, value, and connection of the component that will correct the power factor to unity. I guess we don't need the value of that inductor. I'm just going to tell you what it is, regardless. I'm just going to go there. Okay. So if we have a negative J that, and we said it's an inductor, right? It's going to be negative J omega L. Okay, these cancel out. It becomes beta equals 1 over omega L. So that means L equals 1 over omega susceptance. Does that make sense? Did I go a little too fast on that? Are we good? Yeah. Do y'all agree with me there based on this derivation here? Yeah. Yes? No? Any other questions? No? Okay. So that when you plug in 4 for omega, and susceptance is that, I'm just going to write it out. What am I going to do? 11 equals 1 over 4 times, 11.67, no, 11.76, sorry, 5 times 10 to the negative third, because it's milli. L becomes then 21.25 henries. Well, I shouldn't do that. Okay. We found what the equivalent inductance value would be. There. Yep. Okay. So we denoted that we need a capacitor, right? We need a positive. Oh, actually, I'm sorry. Why did I not make this negative? Well, technically, I did this, right? We had that negative susceptance, as in we denoted it's a negative susceptance, so we've kind of already canceled out the negatives and stuff like that. Basically, the negative part of either your reactance or your susceptance tells you if it's what component it is, and that's all it does. So we've canceled out the negative part. So you only need the absolute value of that. So if you ever have a negative value in your equations to find capacitance or inductance, you're wrong. You also can't have it, like he was saying, you can't have a negative inductance. I think if you had that, physics would be broken. But I don't know. So we found that. Okay, now we do the flip side, which is the capacitance, as in this. Okay, we have a negative susceptance, so we need to cancel it out with a positive susceptance. So J beta equals J omega C. Omegas cancel out. To find C, I'm sorry, J's cancel out. To find C, which becomes beta over omega. I'm sorry, susceptance over omega. Sorry. So capacitance equals that 11.765 5 times 10 to the negative third over 4. C in this case becomes 2.941 millifarads. Actually a really large value for capacitance, but yeah. Well, we have the type of component, as in we have a value, we have a capacitor. We have the value of the component, which is what I just wrote. What is the connection? When you think of connection, what type of connection? What do you think of? Exactly. So how I like to think of this, right? So I'm going to draw a diagram. This is Russell's drawn diagrams before. It's probably in the solution that you have. It is in admittances. So therefore, when you add them in parallel, it's like adding resistors in series. Do y'all agree with that? Okay. Well, so you have those here, right? If you were to add this up, it would just literally be just G plus JL, technically. Sorry. Um, I don't like that either. I like that. Okay. Y'all agree with me there? Yes? No? Maybe? Okay. Um, how I like to think of this is, well, actually, what is y'all's gut reaction? Add a capacitor in series or add a capacitor in parallel? Series? Anybody else? Anybody disagree? Anybody agree? Looks like a lot of people are agreeing. I disagree. If you were to do that, put a capacitor in series, okay, that'd be like doing this. That's like adding two resistors in parallel, which is not what we want to do. We want to do this. We want to do that. So these cancel out and we're just left with G, A, B. So if we were to put that capacitor in series, it wouldn't work. So we need to put it in parallel. Any questions? I see some confused looks, but might take a sec. In terms of admittances, when they're in series, they add up like they're, I'm sorry, when they're in parallel, they add up like resistors in series. Y'all agree with me there, right? So if we were to have that in series, if we were to have this capacitor in series, it would mess up that adding. We'd add these together like they're in series. But then if you were to have that capacitor here, it'd flow up the addition. Well, we're taking at that point we're just taking the impedance or admittance of it, so it doesn't matter. You're adding it like it's either impedances or admittances.
But what you're saying is like, uh, because because GAB in the current state where they're in parallel, the way
Yep.
they are now, GAB and LAB are adding together. They're summing together.
When they're in admittances, that's probably one thing I
Right.
left out. I'm sorry. Yes.
But when you're in this, because because capacitors add when they're in parallel.
It's not because they're capacitors. When the admittance of a component is in parallel,
Okay.
you add it like resistors in series. Right? Do you get what I mean there? Like, so resistors, right? Uh, those are ours. You agree with me there?
Mhm.
Okay. Well, that doesn't work when they're in admittances. If I wanted to find the total admittance, I'm just gonna call this Y1, Y2, Y3. YT is simply. So I'm trying to do the same thing here to where I find the admittance of the conductor, which is just conductance. I find the admittance of the inductor, which is negative J over omega L, and I find the admittance of the capacitor, which is J omega C. And theoretically, these would cancel each other out. These would be the same value, so they cancel each other out. Does that make a little bit of sense?
Exactly.
Yep. There's another issue though. Yeah. Oh, why I just call it power factor correction. You can call it CAB if you want. That capacitor is correcting the power factor, is making that power factor equal to 1. So it is correcting that power factor. So that just stands for power factor correction. That's just how Russell's denoted stuff before. If you want to call it something else, you can call that. But yeah, you could do that if you wanted. Um, I was talking to Pablo with this earlier, and it doesn't really make sense to have, if we would have found that this has a positive, if we would have found that that becomes a positive, right? We would denote that as a capacitor. You'd agree with that, right? So therefore, we'd have to offset it with an inductor. It doesn't really make sense to have it in parallel. Inductors in parallel don't really make sense. And capacitors in series, in terms of dealing with these type of problems, don't really make sense. How can components work? Inductors at a higher frequency, it just acts like a short, and a capacitor at lower frequencies act as an open. Because of that, the connection of a capacitor in series or an inductor in parallel doesn't make the most sense. I've looked at previous Russell problems, and he's either given it to where you have, if you found driving point impedance, it'll be negative, a negative reactance, or if you find driving point admittance, it'll be a negative susceptance. So he's only ever had it to where, with this, he's only had it to where it's either this or this. He's only, that's not supposed to be that. He's never really had a positive reactance or a positive admittance. I could be wrong. And in that instance, like if this was a positive susceptance, right? Or a positive reactance, as in if it was a J omega L that this became. It makes sense in my brain because you're adding it like their impedances or their admittances to put a cap there in series, but it makes sense in my brain in that instance. But the flip side is in terms of frequency, it doesn't really make sense. But I would probably just go ahead and do this because sometimes it's more of the like component adding. That's what I would do. But yeah, did that? I don't know if that helped whatsoever. If that confused you more. If anybody has any questions, please just ask them because I probably confused myself. But yeah, any questions at the moment? The connection part, it's always up in the air. But the previous way of telling you, as in this, since it's a negative susceptance, it's going to be an inductor, and because of that, we have to offset it with the capacitor. And on the flip side, since this would be a capacitor, as in a negative susceptance or negative reactance, sorry, we'd have to offset it with a positive J omega L. Like, when is y'all's problem set due? The problem set that is over complex and three phase. Okay. Look at those solutions for single phase, because a couple of them are going to give you a negative susceptance, and a couple of them are going to give you a negative. I'm sorry. When you solve those problems in terms of Russell solutions, he's either going to find them in driving point impedance or driving point admittance, and they're going to usually be negative, both. So you'd either offset it with the inductor in series for the ZDP or capacitor in parallel for the YDP or DP. Look at those. If you have any more questions for me, let me know, or Pablo. Pablo and I kind of came to an agreement of the adding the power factor thing. But yeah, just ask either one of us whenever you see us.
Can you tell based off of the original circuit that you're given?
No idea. I have no idea.
Okay. I was just wondering, how did you arrive at the inductor and the resistor in parallel with each other?
YDP. YDP. Since it's negative, inductor. And since they are in since they are admittances, they're going to be in parallel. Because we denoted the whole this thing, right? You add two admittances like they're in series for impedances. So these would basically add together just like simple addition because they're in parallel and they have to add together to get this value. That makes sense? Any other questions on this one? No? All right.
Is there a particular section in the materials that you referenced or anything to?
I'm more of, I was looking at the solutions for this one and I was going through it and I was like, okay, that makes sense, that makes sense, that makes sense. Oh, it's their impedances, so they're gonna be in parallel. It was kind of just going through those solutions and trying to gather from that. That's kind of what I did. I would highly recommend doing that before this test.
Sure.
Even if you wanted to, you could have him out on the test. He doesn't care. Y'all know, just literally, you can have all your electronic devices out. Just don't text anybody during it, right? You know, you can do that. Yeah. Okay. Any other last minute questions? I'm going to move on to the final question. All right, cool. The last question is two ports. This is a two-port network. I would highly recommend reading your problem set as well. Your problem set has literally just two-port parameters, which is shocking to me because in my semester and last semester and previous semesters, there was two-port networks and models, or like networks and parameters. This is a network. This is a two-port network. Y'all have never seen this before. So I'll kind of go through how to do it. This is all the information on what I'm about to show you is given in this materials here. I think it's materials 9. Nope, materials 8. Two-port definitions. That is the PDF. Okay. 1996. That okay. I'll kind of just reference this in pages and stuff like that as we go. I don't have any at the moment, so I'll have to scroll through. Okay. But let me go ahead and just read the problem. A resistive common terminal two-port network containing current controlled voltage sources and current controlled current sources is shown in figure 3A. Using the component values as shown, derive and express the numerical form for open circuit impedance parameters matrix ZOC. Express this matrix in the usual form of as it's shown. From this element values in the matrix, calculate the component values from the single source T model shown in figure 3B. Draw this model and label the components values, whatever. Okay. What does this kind of look like? So this is a two-port problem, right? This is a two-port network problem. This is how we're gonna go. We're gonna analyze this to try to get to look at like that. That didn't sound like English, but we're trying to get from the top thing to the bottom thing. And we're gonna do that by trying to get this type of matrix here. What does that top network kind of look like? Like, what are some tools you think you could analyze that from? Just like you use MAME, you could probably use NAME. Well, what does MAME need? You need voltage sources, you need resistances. Okay. Or you could use NAME, which is conductances and current sources. Well, we have these two voltages here, right? Theoretically a voltage source. We have this voltage source here and we have this current source here. Okay. You said MAME. I like that. I'm going to use MAME. Does anybody else have any opinions on using NAME and MAME? No. Okay. Well, what is step one in terms of using MAME? Correct. We have a current source in series with a, well, let's here we go. Okay. We have a current source in series with a resistor, parallel. And we can then turn that into what? Exactly. So I'm going to redraw this real quick. It's going to be really bad, but whatever, I don't care. R1, R3, R2, this becomes positive, that becomes positive there, minus, whatever, that's positive. This becomes, what is the equation then? What does this source become? We had that R2 in parallel. Yep, I agree. Sorry. So then also we want to turn these voltage V1s and V2 into just some kind of like what's the word? Source, arbitrary sources. That's the word. That's the word. Okay, so we have V1, V2. So we've denoted, actually not we, the circuit is denoted as I1 goes that way and I2 goes that way. That's supposed to be I1. Okay. I'm going to say my IMs are going to go this way. I like denoting it that way. If anybody else likes denoting it the other way, you're more than welcome to do so. That too is way far out. Okay, there we go. Okay. So I'm just going to do the main real quick. R1 plus R2, negative R2, 2R2 plus R3. I am 1, I am 2 plus, I'm gonna separate these into dependent and independent. V1 and what it, oh, that's not supposed to be a plus, that's supposed to be an equal. Is V2 positive or negative? Let me redraw all this. It's really small. Is V2 positive or negative? Plus is on top, negative is on bottom. You saying it's positive? Is anybody, you said negative? I agree it's negative. How I always say it is if I have my direction of current, if it goes into the plus, it's negative. If it goes into the minus, it's positive. It's kind of weird. It's
Basically just whatever term leaving.
the way to do it. Yeah, yeah. If it's leaving the negative, it's going to be negative. If it's leaving the positive, it's going to be positive. I like that.
It's just like the arrows too. It's like if they're going against, if they're pointing against each other, then it's negative. If they're flowing with each other, then they're adding to each other.
Exactly. Another way to put it is current goes from high to low. If you kind of go out to in, it goes from high to low. If you go out to in terms of this one, it goes the opposite in terms of low to high. So therefore it'd be negative. But I like the way you put that. So that means this would be a negative V2 plus, same thing here. Same thing here. I'm going this way. It is exiting positive. So therefore it's going to be what? Exactly. And then if you keep following that arrow, it's exiting the negative. So therefore it'll be a negative R2 alpha I1. Yeah, alpha. And then if you do the same thing here, exiting the positive. So therefore this can be an R2 alpha I1. Okay. What is I1 in terms of mesh currents? I have this denotation. Word. Denotation, there we go, of IM1 going that way and I1 goes that way. So they are exactly. Well, I1 equals positive IM2. All right, IM1. Yeah. Okay. Same thing here. IM2 I have going that way. I2 I have going that way. So I2 equals what? Exactly. Yep. So that means this is V1 plus RM, bless you, negative RM IM2 plus R2 alpha IM1, and this becomes, why did I put a positive? That's supposed to be minus. R2 alpha IM1. So then that just becomes V1 plus negative R2 alpha, because it's with IM1, negative RM, and this becomes a positive R2 alpha 0. IM1, IM2. So that final matrix then becomes R1 plus R2 plus alpha R2 minus R2 plus Rm, then negative R2 minus R2 alpha, and R2 plus R. IM1, IM2 equals V1 negative V2. Okay, you agree with me there so far? Everybody? Yeah, yeah, okay. So then, go in here, plug in the values for everything, you get 4. Give me 1 sec, sorry. Yeah, okay, cool. Yep, that's correct. Okay. IM1, IM2 equals V1, V2. Okay, so we used main. Would this give us impedance or admittance based on my earlier derivation? It's up top. Would that give us impedance or admittance? I agree. So this would just give us admittance. I'm just going to say that. We are finding our open circuit matrix. Okay. Let's see if I can. Excuse me. We will be finding in admittance, as we just said. So as you see, there's some impedances and stuff like that. I'm gonna skip that for right now and find this. Okay. So here is something from that 2-port definitions. This is what was that? What did that say? That said chapter page 22. For the short circuit impedance matrix, which we will be finding, but we can find that out shortly. We will find all the components of that matrix using these formulas. Y11 equals this, Y21 equals that, Y22 equals that, Y11, Y2 equals that. Where the ones and twos, the first digit is what of our matrix? Our rows or our columns? Row. And what is the second one? I agree. So Y22 would be second row, second column. Y12 would be first row, second column. So we're doing this to where we're putting I1 over V1 when V2 equals 0. Okay? We have this. We have our arbitrary sources. This is kind of like a Thevenin's or a Norton's. In this case, it'd be a Norton's because we're using main, where we turn off the one source, we turn on the other source. It's kind of like that, to where we have the arbitrary source. But instead of having a 1, we just have an arbitrary source. So what I'm going to do is I'm going to plug this into the calculator where I have a V1 and a V2 in terms of just the actual variable. I know I'm not going to put any values. And so I'm going to say for the first one, Y short or I am when V2 equals 0. So that means I am 1, I am 2 equals V1 divided by 5 and V1 divided by 5. Literally all I did was I did the whole, this is A and this is B, and I did the I n equals A inverse times B. Does that make sense? Anybody? Yay, nay? Does that sound familiar to anybody? Like I literally just made a matrix in my calculator, and then took the inverse of that matrix. I made this matrix in my calculator, took the inverse of it, and then multiplied it by this, to where there's a V1 here, and the V2 is 0. So then my IMs are now in terms of V1s. Anybody got any questions on that? Yay, nay, may, maybe? No? Okay, I'm gonna move on. So then, now I'm gonna do the flip side. When V1 equals 0. That then becomes IM1 and IM2 equal to V2 divided by 15. And then this becomes negative 4 V2 over 15. Okay, this is our IMs in terms of voltage. Okay, so as given by this formula here, okay, not that, here we go. Y11 equals I1 over V1 when V2 equals 0. So I'm going to be looking at these here. So that then becomes IM1 over V1, which then becomes V1 divided by 5 over V1. So that means Y11 equals 1/5 Siemens. Does everybody see how I did that? Kind of? Yay, nay, maybe?
Feedback. Where are you getting these numbers?
So
Does that have to do with anything?
yes, it does this. So I made a matrix in my calculator. 7, 1, 1, 2 rows, 2 columns. 4, 1, 3, that's a negative 3. Took the inverse of it. Some of y'all do row reduced echelon form. Does that sound familiar to some people?
Yeah,
I don't do that.
I like the negative.
Okay, yeah, I don't do that, where I think the row reduced echelon form would be, it's confusing to
I think you
me.
just type REF with an open parenthesis.
Yeah, yeah,
Reduce, resistance matrix first, and then you plug in sources.
Yep.
On the last row.
yeah. So you do that, and then I don't know what the outcome of that is, but
If you hit enter, there should on the
so,
on the
okay,
website
so
will be reduced to like a diagonal matrix.
so technically I need to make a 3 by 2.
A 3 by 2.
Okay, cool. Let me try that. I've never done this before, so. This just, oh no, 2 by 3, sorry. Okay. So you're saying type RREF?
Yes.
Yeah, I mean, I think it's parenthesis.
Yeah,
I think.
and then, yeah.
And then you parenthesis.
So this would theoretically be 4, 1, negative 3, and 3, and then I'd put V1, and then negative V2, and then I hit enter. Oh,
And then the answer is IM1 should be the top row, IM2 bottom row.
I see that and I hate it. It's the same answers, but I hate it. Because literally I could just do 1, 7, 7, no, not that. Nope. 7, 1, 1, create a 2 by 2 matrix.
It's quicker because you only need to make one matrix. And
I agree, I just don't like that form.
Hit the reduce.
Yeah. Yeah.
Low.
So what I do is, yeah, the negative 1, and then make another matrix. Nope, I keep doing the same thing. There we go. So then you'd put the V1. Oh, I see why you're saying in terms of it's faster. I just don't really like that. So when I do that, if anybody's curious, I have a V1 over 5 and V1 over 5. It is the same. Oh,
I don't ever know. I'm sure it's how I've got my answers and everything set up for the page.
so a couple things. We turn off that second voltage,
Okay.
but yeah, you mean you get the same thing.
And maybe the page formatting.
Yeah, I
Is what
think
I'm
it
thinking.
is. Yeah, you have an engineering shouldn't do anything. Is this your own personal or IEEE?
Yeah, no, it's my first.
Okay.
Those, the problem is like there's no just one set of settings for the page that I have to keep it in, that it'll just be good for every problem.
Yeah, that's the only sucky thing.
To me, or at least for me, that's probably one of the biggest learning curves of using that calculator is figuring out what I need to have my calculator set for.
I put it, you had this,
That I have for approximate
yeah. And I put it into auto.
auto.
Now you could theoretically do the same thing.
Yeah, but I like the clean version a little better.
And so if you were to do the same matrix and substitute that V1 with 0 and substitute that 0 with negative V2, you'd get the answer that I have. You could also just copy paste. I love that on this freaking calculator, man. I absolutely adore that. Okay. Everybody else good? Yep, okay. So like I said, y11 equals I1 over V1, where V2 equals 0. So then I just look back at this matrix here, which is this top one, right? And I have that. So then I1 also is IM1. It's positive IM1. I'll tell you why in a second. So V1 over 5 over V1. The V1s cancel out, and I just get 1/5 Siemens. Okay. Does that make sense? Yeah. Yeah. Oh, okay. I1 over V1 when V2 is equal to 0. I have found that by this equation here. You agree with me there? Okay. Yeah, I keep going with the freaking wrong thing. Okay, so I1 equals IM1. The V1 is still there. We can't do anything. So I go back up to this equation. IM1s when V2 equals 0, right? And so IM1 is that V1 over 5. V1 over 5. And then that V1 just cancel out the V1s. And so our Y11 term becomes 1/5. Sorry. That is Siemens. Because we're at minutes. So then the next thing on this is Y21, which is I2 over V2 when V2 is 0. Let me go back to let you look at it. Oh my God. What the, okay, I'm just gonna do that and that. Cool. Okay, so 2, 1 equals I2 V1 when V2 is equal to 0. Well, what is I2 in terms of nodal currents? I mean, not nodal currents, that doesn't make sense. Mesh currents. So negative or a positive? Negative what? Negative IM2. So that then becomes negative IM2 over V1, which then equals, it's also when V2 is equal to 0, so I'm going to look here. Does that make sense? Okay. So IM2 is a negative 4 V2 over 15.
It should be the first,
Zero, so it should be
Yeah.
first matrix.
because you're doing when V1 equals 0.
I'm just testing you guys. V1 over 5. Yeah, I agree. I don't know why I even did that. Over V1. So that means that Y2, 1 equals negative 1/5 Siemens. You agree? Does that make sense so far? Yeah, no? Yeah, okay. So next, I'm gonna look at that document. The next thing is Y22, which is I2 over V2 when V1 is 0. And this is page 23 of that. So Y22 equals I2 over V2 when V1 is equal to 0, which equals negative IM2 V2, which equals, now I can do that, negative 4 V2 over 15 over V2. Cancel, negatives, that becomes positive, so V22 equals 4 over 15. Cool. And then last but not least, V12 based on this equation here. So I1 over V2 when V1 is equal to 0. I1 over V2 when V1 is equal to 0. So that then becomes, I go back to this matrix here, V2 over 50. Oh, I'm sorry. M1 over V2, which equals V2 over 15 over V2, right? Yeah. So that means Y12 equals 1/15 Siemens. So now we just plug it in. Y11, 1/5. First row, first column. Y21, -1/5. Second row, first column. What the heck would that be? Right here, sorry. -1/5. Right? Yes. Y22, second row, second column. 4/15. And last but not least, 2-1, 1/15. We got a short circuit. Well, that doesn't fully help us because we want open circuit impedances. How do we find that from what do we have? From what we have? We have, yep, which you kind of can't do that in terms of matrices. So Z open circuit equals the, yeah, open circuit. No, it's literally, you can just do that. You just put it, you create a matrix, 2x2 matrix, put these numbers in, literally take it to the -1, and you'll get 4, -1, 3. Literally it. But we're not all the way done. We've got our open circuit impedance matrix, as you see. But we want to find, so we have this, which is kind of right, but we want to find the single source T model, as in this. So we need to find RA, RB, and RC, well, RD, and RA, RB, RD, and that value for RC. Okay. Well, we go to our handy dandy materials. We're technically in the impedance part, which I'm just going to let you know was after the admittance part. So I'm sorry. We're in the admittance part. Impedance was before this, so we need to go up to, where is it? Where is it? I think I passed it. Page 20. ZA, same as RA. Impedances, resistances, whatever. So I'm going to use those equations. Z12 equals, I'm sorry, ZA, Z11 minus Z12, which equals 4 minus -1. ZA equals 5 ohms. ZB equals Z12, which ZB then equals -1. ZB, oh, sorry, let me just, that was from here. Second. So now I'm looking at this. I wouldn't really look at this. This is crap I don't want to look at. Z21 minus Z12 equals ZC. So that then becomes 3 minus -1. ZC equals 4 ohms. Z D, based on this equation here, is Z22 minus Z12, which equals 3 minus -1. ZD equals 4 ohms. So we have found all those parameters, and we are done. Well, yep, that's all I got for y'all. Any other questions on anything else? Does this make sense so far? It's literally just looking through the materials. The two materials that I have, the active filters, book through chapter 3 for 2 ports, 2-port definitions. Those are both in materials 7 and 8. You might be actually right. 8 has 2 ports. 9 has Salem and Key. So you were right. 8, 2 ports, 9 filters. So. Yep. Yep.
Instead of drawing admittance, can I convert it to impedance and draw that instead? Would that count? Because I realized the connections, no matter if it's impedance or admittances, we still put capacitors in parallel and inductors in series.
Maybe that's what you do. Maybe that's what you do, period. I think that's what it is.
Yeah, because even if it's admittances, you still put the capacitor in parallel.
Yep.
And if it's inductor, you still put it in series.
Yep. Yeah, okay, yes, what you said, yes, so,
So basically the component determines the connection type? Is that what y'all are saying?
yes, yeah, if you need a capacitor, um, if you need a capacitor, it's gonna be in parallel, and if you need an inductor, it's gonna be in series, yes, yes. What you're saying, I believe, is true.
So then basically, as soon as you get the numerical value, then you should already know the component and the connection type.
Yep.
Essentially.
Yep, um, you know, I'm just gonna, I don't wanna write it out again, I'm just gonna look at this. In terms of this. Put it back in here and then read it. Okay. Negative susceptance. It's going to be basically an equivalent inductor, which we recently went over. So you need, I said equivalent here. We'll put power factor correcting capacitor. Equivalent or positive susceptance is an equivalent capacitor, which we derived earlier, which means you'll need a power factor correcting inductor. As you said, flip it into, in this case, if you're trying to find the equivalent inductance, you can flip it into impedances and find it that way, but it's going to be in series, like you said. Here, negative reactance is going to be an equivalent capacitance, which we agreed from the derivation, and then it's going to be the same thing here. It's already in series, whatever. Positive reactance is going to be an equivalent inductor. You're going to need an equivalent capacitor, flip it into impedance, admittances, figure it out from there. So I guess that's a better way to put that, yeah. Materials 8. Yeah. Book 2, chapter 3 is materials 8, and 2-port definitions, materials 9. At least it is for me. I took it a year ago. It should be the same for y'all. Should be the same for y'all. Which one? Open circuit? So literally all I did was I took this matrix, I plugged it into a calculator, took the inverse of it, got the. Let me double check, but I'm pretty sure I got this. Yes, give me a sec. Yeah, I got these guys. What's up? You mean like up here? Maybe the negative IM2 is messing you up. So yeah, it's denoted as I2 and V2, I2 and V or I2 and V1 here, and I2 and V1 here. But as we denoted earlier, by the direction of my mesh currents, I2 is equal to negative IM2. Which one are you stuck on? Which one are you stuck on? Or which one isn't the same? Which one? Y22? So the actual value here is a negative 4 V2 over 15. And so when you put a negative and the negative or negative 4, or the negative of IM2 and -4 V2 over 15 becomes a positive. Can I see your calculator? No problem. Yep. Anybody got any more questions or anything?
This is called two-port systems.
Two-port networks.
Two-port network.
Did you, when you took a photo of what he put for that test, was networks one of the two-port parts? Yeah. Like you took a photo of the topics that were gonna be on midterm too? Apparently he's done with y'all stuff, which is crazy. Okay, this would also be classified as models.
So
Yep. So I'm gonna go ahead and stop recording. So this is currently, this meeting was in the HCAN teams. If none of y'all are in it, I have a link to that in, the Discord for UTA EE and the Circuits 2 thing. But hopefully sometime this semester, this review will also be on YouTube. If anybody is curious for the final in terms of wanting to look at previous reviews, you can go onto the HCAN YouTube channel. You can search through that and there should be spring 2025 or fall 2024 Circuits 2 reviews. That's when I've done, those are my 2 reviews. So you can look at all that. But I'm gonna go ahead and exit this out.